What do we need to know about it? Okay, because this is the first chapter that's really on chemistry, like I said. And yesterday we only talked about the history of the theory of some famous scientists. Not famous to you, okay? It's not the Kardashians or anything. But famous enough for scientists. All right, well, you already know most of what I'm going to tell you. I'm just going to kind of go into a little bit more detail, and then we're going to do some problems with it. A lot more problems, a lot more detail when we get to the math part of it. Okay? First of all, the modern atomic theory says much of what Dalton said. All matter is composed of atoms. That's what Bill Nye said. All matter is composed of atoms, but we now know those atoms are made of smaller particles. Okay? And the crazy part is, protons, neutrons, and electrons are made of smaller particles, quarks and crazy things that you really, I don't understand. You want to become a nuclear physicist and delve into the atomic theory in detail, you can. But, that kind of stuff gets really weird once you get down to that level. We're going to keep it relatively simple and talk mainly about these three: protons, neutrons, and electrons. And of those three, chemistry, see, physics is going to deal more with the protons and neutrons at the subatomic level and then what they're made of. Chemistry, it cares almost 90% of chemistry has to do with this guy right here, electrons. And you'll see that as we go on. As a matter of fact, next chapter, guess what the next chapter's on? I'm going to spend this whole chapter on the entire atom. Next chapter is only on electrons because that's what makes everything happen in chemical reactions, electrons. All right, we'll get to those. Let's start out with, before I get to that, the number and arrangement of these particles, protons, neutrons, and electrons, gives each individual atom its own unique properties. See, that's what's different from, for example, Democritus, Dalton. These guys didn't really understand. They assumed and basically proposed that there was this indivisible particle, we'll call it an atom, but they figured each one was unique. You couldn't divide it anymore, but each one of those atoms is unique. In fact, they are unique, but they're made of stuff that's the same. All right? A carbon atom is made of protons, neutrons, and electrons. It's just the number of protons, neutrons, and electrons that gives that carbon atom its properties. Carbon has, if you take a look up there, see up there in the periodic table? Carbon has 6 protons. You can tell that by the atomic number. We're going to see it in a minute. What makes him carbon is that those 6 protons. You add a proton to carbon, and he's no longer carbon. He's nitrogen. He's a gas. He's a totally different guy. He's not the same atom anymore. So it's the number and arrangement of the protons, neutrons, electrons. It's not that each individual atom itself is a separate thing. It is unique, but it is made of the same stuff. All right. Let's start with the electrons. Because like I said, they're going to be the most important. Electrons, and a lot of this I'm going to say in the beginning, you already know. I'm sure you already know electrons are negatively charged. You've heard this before. You made your models back in elementary school, middle school. Remember making models of atoms? You had the electrons flying around outside of nucleus. Okay, they're located outside of nucleus in orbitals, electron clouds. Okay, energy levels. We're going to talk about all that next chapter. I'm going to get into a lot more detail about. For now, we often see the atom drawn like this. Even Bill Nye did a couple of things like this. I don't like it, but you'll see this. That's a pretty loud symbol. Let me do a better one. Okay, like that's the symbol for atomic. Don't draw that. And it kind of assumes that the electrons are going around the nucleus like the Earth goes around the sun. Okay, that ain't true, but it is true that they are outside the nucleus. So we'll talk about how they go around the nucleus next chapter. Electrons are very light. They're about 10,000 times lighter than a proton or a neutron. But even though they don't make up a whole heck of a lot of the mass of an atom, they're responsible for the vast majority of their volume, of the volume of an atom. Because they circle the nucleus. They orbit, I should say, not circle. They orbit the nucleus. All right, they go around the nucleus, and they fill up a large space, kind of like Bill Nye uses as an example. It's not a great one, but it's pretty good. A fan blade. Most of the fan is empty space. But when you spin the fan, it kind of fills up that space. And that's what happens with an electron, okay, because it's moving near the speed of light. Very, very fast. All right, so electrons, those are the main things you probably already knew about an electron. Do you remember what you call a guy if I change the number of electrons? What's he called? I can remove an electron. It happens all the time. You ever get a carpet shock? You ever get an electrical, you touch a doorknob on a dry static electricity? You're removing electrons. You're rubbing electrons off. It's easy to remove electrons. Not so easy to remove protons and neutrons. What do we call an atom that has lost or gained electrons?
Isotope.
Not an isotope, but that's the common mistake. Begins with an I, though.
Isomer.
Not an isomer. An I have my eye on you. Exactly, it's an ion. Yeah, it's one of the I words, and it's ion. All right, so an ion is a charged atom that has lost or gained electrons. It's not so hard to lose or gain electrons, and if he does lose or gain electrons, he's still that atom. A sodium ion is still a sodium atom, still considered sodium. It's just lost an electron. A chloride ion is still chlorine. He's just gained an electron. He's still a chlorine atom. He's just an ion of chlorine now. If I take away a proton or a neutron, it's no longer sodium. It's no longer chlorine. Okay? All right. So electrons, they're floating around outside. They don't take up a whole lot of mass, but they are taking up most of the space, and they're responsible for ions. And ions are kind of important. We're going to find in the next chapter when we start to put things together. All right. What about protons? Well, protons, they get paid because they're not amateur tons. They're positively charged. Are you sure? Positive. Protons are very sure of themselves. They're positive all the time. I hate people like that. Positively charged. They're up people. They're located in the nucleus. They're not flying around out there. They're responsible for most of the mass. Them and the neutrons are responsible for most of the mass of the atom. They're very large mass compared to the electrons. Not much different than a neutron, though. Very close. Neutrons just a tiny bit more. And there's a big thing about protons that you need to know. There are several terms I'm going to give you today. I underline them and put them in bold. You might want to do the same. Ion was the first one, besides, obviously, proton, neutron, electron. Ion was the first one. Here's the next one. That number up there I told you about. Look at carbon. I'm going to use carbon, sodium, and chlorine a lot when we're beginning this discussion of atoms. Look at carbon up there. That 6 is called the atomic number, and it is the number of protons in an atom. That's a really big deal. That number for any given atom cannot change, or it makes it a different atom. It's no longer that atom anymore. Okay? It's different for every element. That's what makes an element different from it. Bill now was banging on the copper and whatever. He said, what makes those two metals different is the fact that they have a different number of protons. Not the fact that it has a different number of electrons. Not the fact that it has a different number of neutrons. It is only the protons that determine the identity of the element. I can lose or gain electrons. I can lose or gain neutrons and still have the same element. Just an isotope or an ion or whatever of it. So that's a big deal, the atomic number. We're going to come back to that. Now, this last thing I'm going to talk about is neutrons. And as the word implies, neutrons, neutral, they don't have a charge. They are also located in the nucleus with the protons. They have almost the same mass, like I said, very, very similar mass to protons, and a very small volume, very dense particle compared to an electron. They're not responsible for most of it. Remember what I said about the atom. The size of a soccer field, the nucleus, all those protons and neutrons be smashed together into the size of a pea, even though the atom's the size of a soccer field. And one more thing about neutrons, I should say. What do we call, I heard it here before a minute ago, what do we call guys who have lost or gained neutrons, but they're the same atom still?
That's one on the one side.
Which is it, though? Guess.
Isotope.
Isotope is correct. Isotope. Iso as a prefix means same. All right, we're going to say isomers, isotope, isotonic solution. Remember isotonic solutions from biology? It means similar or same. Isotopes are the same atom, but they have different numbers of neutrons. All right, so that's a basic description of the three main particles we're going to talk about throughout this year. Okay, we're now, modern atomic theory knows that there's more stuff than there is to this. There's quarks and all kinds of crazy things, and there's all kinds of theories out there. But these are the three things we're going to really concentrate on. We're not in college. We're not in nuclear physics here. They're the three ones. And if you know how to use these to do the calculations and the predictions, you can predict a lot about atoms and a lot about chemistry. All right, one last thing, I want to put together something here, and that is something called the mass number. The mass number doesn't fall necessarily underneath protons, neutrons, or electrons. The mass number is the number of protons and the number of neutrons added together. And I'm going to use that to identify specific isotopes of an atom. I'm not going to do that today. Actually, I'm going to stop in a few seconds and let you start on what little homework you have that encompasses stuff from yesterday and today. It's right up here. I'll put it on the board here, too, for people who are absent. But I'll start the actual calculations. We'll have time to do them in class on Monday. But I want to just finish with something here. Copy that down. Because these new terms, let me explain them to you a little bit, just using the periodic table. And so everybody can see it, I'm going to put get a periodic table up here. I know I've got one somewhere. There it is. Well, it's not a full one. Use a whole one. All right. So you know what? The reason I had that one is so you can see it actually on the periodic table. All right. There's a whole periodic table, right? I want to say a few words about these guys, but I'm going to zoom in on one part. Okay. Over here, so people can see them. So that's zoomed in on the right side here. Okay. Of the periodic table. Let me say a few words about this. If I asked you, what's the atomic number of chlorine? What are you going to tell me the atomic number of chlorine is? 17. Okay? If I asked you what the mass number of chlorine is, what would you tell me? You'd say 35.453 right now. It is not. That's why I'm doing this right now. There's a couple things I want to point out to you. That is not the mass number. That's something we're going to talk about probably on Monday, the second period. Something called the atomic mass. It can't be the mass number, guys. Can you give me one reason why, logically, 35.453 cannot be the mass number? What's that? Yeah, it's a decimal. What does the mass number have to be? A whole number. It's just the number of protons plus the number of neutrons. That is not the mass number. It's something called the atomic mass. We're going to talk about that on Monday or Tuesday. Secondly, let's take a look at carbon again. What do I call carbon? What do I call carbon if I take away an electron from carbon? What do I call it? What's the word? No. Take away an electron. An ion, right? If I take away an electron from carbon, I call him an ion. And what charge would he have if I took away an electron from carbon? What charge would he have? What charge do electrons have? Negative. So right now, a neutral carbon has 6 protons and 6 electrons. If I take away one of those electrons, what charge would he end up having? Everybody agree it would be +1, right? What if I add an electron to carbon? What do I call him? He's still called an ion, right? But what charge would he have? A -1. What if I added I could add 2 electrons to carbon. What would he be? Negative what? -2. All right. What happens if I take a neutron away from carbon? Would his atomic number, this is the atomic number, would it still be 6? Yes. But if I take away a neutron from carbon, what do I call him? An isotope. If I add a neutron to carbon, what do I call him? An isotope. Okay. Does he have any difference in charge? No, because neutrons don't have charge. What happens if I take away a proton from carbon? I get boron. Exactly. I get boron. Okay? All right, so there you go. That's why I just want to summarize all that stuff with you. That's the kind of questions you're going to get a little bit in tonight's homework and some from yesterday with the history. I'll put that on the board right now. Okay? Page 107, numbers 15 to 20. And page 110, numbers 23 to 28. Okay? Get working on those. You probably will have no homework. You have about 10 minutes. It won't take you much more than 10 minutes to do that. That's how easy the stuff is.